infinity, most students get confused. If I said to you, add up all the terms to infinity, you're going to look at me and say, you need psychiatric treatment. How on earth am I going to add up all the terms to infinity? Because infinity is like a never-ending story. So what am I going to do? It's actually a bit deceptive, that sum to infinity. I prefer to talk at it in terms of limits. Okay, what does this mean? So let's explore sum to infinity a little bit. Don't say you're adding up all the terms to infinity. Impossible. You're never going to stop. So what does sum to infinity mean? Let's have a look at this. I'm going to take what we call a convergent geometric series. Okay, now look at this. This is convergent because it kind of goes down, but there's a set thing that's happening. The first term, of course, is a half. The constant ratio is a half because you keep multiplying by half. Now watch this. If I say, let's start with the sum of the first term, what do we mean by sum of the first term? Well, we take, there's no terms, you bring a term in. So the sum of the first term you bring in, there's nothing there, so add in a half. So what do we have as a half is 0.5. Okay, now the sum of the first two terms would be a half plus a quarter. Now a half plus a quarter is 3/4, which gives me 0.75. Okay, the sum of the first three terms, well, first term, second term, third. Well, if you use your calculator, this works out at 7/8, which converts to 0.875. The sum of the first four terms, now remember we're multiplying by half, so what would be the fourth term? 1/16. And then what's the next term? 1/32, and we're going on. Okay, so the sum of the first four terms, if we add them up, is 15/16, which is this funny looking decimal. Sum of the first five is 0.96875, all done with a calculator. Now look at this decimal. This one, this guy, where are these decimals going to? Well, they're progressively getting a bit bigger and bigger, but it seems like this is getting longer, but this is going to approach. I can almost intuitively think of this as approaching 1. Okay, and I doubt whether it's going to go 1. We say that if the constant ratio is a half, this series, this geometric series, is converging. The progressive sums, the sum of the first two terms, the sum of the first three, the next four, the first four, the first five. Where are these terms? As you keep adding in, they are converging to a limit, which we refer to as the sum to infinity deceptive. It's not the sum of all the terms to infinity, because you can't add up all of the terms to infinity. But what it is it's the progressive sums. Sum of the first two terms, decimal. Sum of the first three terms, decimal. Sum of the first four terms, decimal. Where are the decimals going? They're approaching 1. If Sn is going to approach 1, if the n goes to infinity, if we keep going on, that decimal gets longer and longer, but eventually it resolves out at 0.99999, but it'll never ever get to 1. It approaches. We call it the sum to infinity. And by the way, there's a little formula that you can use. It's S infinity is called A/1 minus R. Now what happens with this? If you look at the first term, it's going to be a half divided by 1 minus a half. Now look at this. A half over a half is actually 1. Now this formula is derived in textbooks. It's quite a complicated thing, but I doubt whether they will really ever ask this. But the important thing is, if you know your A and your R, you can get the sum to infinity, which is not the sum of all the terms to infinity, but the progressive sums. Okay, what's also very important, I just want to quickly show you something. If you have a series that doesn't converge, what if you had something like this? Let's have a look. If I made the series 2 plus 4 plus 8 plus going on, okay, what happens here? So first term is 2, the constant ratio is term. Now watch this. The sum of the first term is 2, you bring it in. The sum of the first two terms is 2 plus 4, which is 6. The sum of the first three terms is 2 plus 4 plus 8. That gives you 10, 14. Where do you think these are going? That's just getting nowhere. It's just getting progressively bigger. We're not converging. What are we doing? We're diverging. It's diverging. It's not convergent. So what mathematicians have concluded, and this is very, very important, when you deal with the sum to infinity, if it's got to be geometric, Very important. It's got to converge, but it converges only if the constant ratio is a fraction between -1 and 1. That's very important. I'm not going to derive this, but it's very important to know that S infinity exists if your constant ratio is a fraction between -1 and 1, and otherwise the series diverges. And arithmetics are never going to, you're not going to converge with that. It's only the geometric, the exponential number pattern that does it, provided that it's going to be a constant ratio between -1 and 1. Good stuff. So here's a summary. It's in the notes. If in a geometric series that holds true, then the series is convergent and the sum to infinity exists and equals this wonderful formula over there. Okay, but it's got to converge and that condition must be met. Okay, so how do we approach this from an example point of view? Have a look at this. Example 21. Read that quickly. It says evaluate the sum to infinity from r equals 1 3/10 to a 10th. Okay, now again, how do we expand this? Well, let's see. Okay, so it's 3/10, 1/10 to the 1 minus 1, which is 0, plus 3/10 to the 1/10 to the 2 minus 1, which is 1. Looks very geometric to me. Okay, 1/10 squared, and that's going on forever. Now, what do we know about that thing? Let's just tidy this up. That's going to be 1, so it's 3/10 plus, okay, 3/10 multiplied by 1/10, okay, plus 3/10 multiplied by 1/10 squared, going on. It definitely means that the first term is 3/10. Now, what do you keep multiplying by? 1 over 10. That's quite easier. In the notes, I've actually multiplied that out. 3 over 100, 3 over 1,000. But look at that. You can see that you're multiplying by, you know, the 1 over 10. Now, what is 1 over 10? Is it a fraction between -1 and 1? For sure. That lies in this restriction here. It's cool. I like that. It works. Okay, so sum to infinity exists. It converges to this thing called the sum to infinity. So what is that going to be? Sum to infinity is a over 1 minus r, which is the a over 1 minus the constant ratio. You use a calculator to work this out. It will come to a third. The series, this thing is converging. It moves down, or even up sometimes, but it's actually moving towards 1 over 3. Now that you couldn't have got intuitively. You need that formula a over 1 minus r. Love this stuff. It's good stuff. Hey, okay. So be careful. They're going to love it. And look at sum to infinity. But remember, it's not the sum of all the terms to infinity. Okay, and this, please, boys and girls. Oh, very, very important. Because in the next example, 22, check this one out now. When students see this, they want to cry. But it's not too difficult. Watch this. For which values of x will the series below converge? Okay, converge. Well, what do we know about a convergent geometric series? Is it geometric? Look at this. The first term is x plus 1. The constant ratio is x plus 1. You keep multiplying by x plus 1. Okay, but the thing is, for convergence, that's got to hold true. Okay, what's the constant ratio? X plus 1. So let's sub it in. And this reminds me of a grade 10 formula. Do you remember in grade 10, compound inequalities? Have a look at this. If we want to solve for x, all I'm going to do is I'm going to subtract 1 to get x on its own. If you minus 1 from everybody, what do we know? This comes to -2 less than x less than 0. So if your x value is anywhere in between there, except, let me make a point here, very important. If your x does, you can't really have it being -1, because if x is -1, the whole series vanishes and you just get 0. So it's very important to state that as well. Okay, so we lie between, if x is between -2 and 0, you have a nice little convergent geometric series where the sum to infinity is actually going to exist. Okay, one more example before we get into some real-world applications. Let's look at example 23. Just read that for a bit. In a geometric sequence, the second term is this geometric, and the sum to infinity is this. find the sequence. Okay, now how would we approach that? That's quite tricky. Okay, second term is negative 2/3. The sum to infinity is 3/5. Okay, now listen to me carefully. The sum to infinity is a over 1 minus r. Okay, so it must be a convergent geometric series. Now look at this. What do we know? We know that Tn is ar to the n minus 1, and we know that S infinity is a over 1 minus r. Now what do we know? We know the n, so that's T2 is equal to a r to the 2 minus 1. What do we know about T2? Negative 2/3 is ar to the 1. Okay, great. There's one equation. This one, the sum to infinity is 3 over 5, a over 1 minus r. And we have another funny looking equation here. This doesn't look too good. But what I'm going to do now is something that's a little bit complex procedure. It's a bit of level 3 in the exams. How on earth do we solve equations like this? Check this one. What I'm going to do is I've got two funny looking equations. What I could do is, if you look at this, I've got AR equals minus 2/3. Now, if I've got this, what I'm going to do, now there's many ways you can approach this. What I'm going to do is I'm going to make A the subject of the formula. You'll see now why. If you've got this, if I divide both sides by R, now careful, this would be the same as multiplying over 1 over R on both sides. This is equivalent to negative 2 over 3R, which gives me A. So there's something for A. Look at this one. You could do a little bit of cross multiplying here. So you could say 3/5 multiply both sides by 1 over R, so that goes up there, is equal to A. Now look at this. You've got A is equal to this, but at the same time A is equal to that. So you could actually equate these two. So you could say negative 2 over 3R is equal to 3/5 1 minus R. Okay, great. Now we could solve for R quite easily here. What is the LCD? Well, it looks like it's 15R. Okay, now multiply both sides by 15R. Let's see, what do we get? Okay, well, the R's cancel. 3 goes into 15, 5. 5 times negative 2 is negative 10. Okay, this is 5 times into 15 goes 3. 3 times 3 is going to give you 9R into 1 minus R. Whoa, what is this? Looks like a trinomial. Multiply in. Okay, a little bit tricky there. Bring it across. Okay, bring that across. Keep the negative 10 there. Okay, so what do we know? No common factor. Now, of course, guys, what can we use here? The quadratic formula, or if you don't have the quadratic formula that you want to use, you can use your grade 10 method, which I'm going to do. But, of course, you don't have to do this. You can use the formula. What do we know? If this factorizes, it's 3R minus 5 and 3R plus 2. Okay, now check. Let's see, minus 15 plus 6. 9R squared minus 10. Of course, use the formula if you don't like this method. So what do we know? 3R is equal to 5. So R is equal to 5 over 3. Or 3R is negative 2. R is negative 2/3. Now, R is equal to 5 over 3 and R is equal to negative 2/3. Okay, people, but now be very, very careful. What do you know about the constant ratio? If the sum to infinity exists and it converges, the constant ratio must be between minus 1 and 1. Okay, now have a look at this. This constant ratio here is going to be 1 and 2/3. 1, 3 is 3 plus 2 is 5. Now this is negative 2/3. Which of those guys lies between minus 1 and 1? Definitely not this guy. This is not valid for convergence. It's not valid at all. It's outside of that. The series will diverge. So what about this one? This guy is nice because why? It's going to be between minus 1 and 1. So that's the constant ratio that we're looking for. Okay, be careful. Many students take both. Don't. This is a really difficult question. This is starting to get to level 3. Now watch this. If we know R, let's look at what's an easy equation. I'm going to use AR is negative 2/3. Where did that come from? Well, from here. Okay, so let's have a look. What do we know? AR is equal to this. What do we know about R? It's negative. This is easy. Now, look here. The R is negative 2/3 is equal to negative 2/3. Divide both sides by that fraction, and A is equal to 1. So what would your series or sequence be? Let's have a look. The first term is 1. Multiply by negative 2/3. There we go. Multiply by negative 2/3, 4/9. Clearly geometric, and clearly the constant ratio is a fraction between -1 and 1, meaning the series converges or the sequence converges. And by the way, what would be the sum to infinity? Let's just check this. Sum to infinity is A over 1 minus R, which is 1 over 1 plus 2/3. And let's just do this. Let's say I don't have a calculator. That gives me 5 over 3, which is 3/5, which is precisely what you needed there. If you look at the question, it gave this, the sum to infinity is 3/5 there. And what is our answer here? Have a look, is 3/5. Okay, so it does work. The sum to infinity is 3/5. Okay, we've got our A and we've got our R. Okay, you happy with that, guys? This is really, really good stuff, and I think it's worthwhile knowing these things.